Hi everyone and welcome to this new video. In this video I continue my Linux Privilege Escalation series. Now in the previous video I discussed about the Linux file system permissions, and in that video I introduced the idea of the set user ID bit, the set user ID permission. In this video we will focus on how we can exploit binaries with this particular permission when they are owned by root. So this is called SUID Exploitation, and it exploits a specific configuration when a binary has the setUID bit on and the user who owns the binary is the root user. So I hope the video is enjoyable. If you have some feedback, please leave it in the comments, share it with like-minded people, and enjoy the video. So to start off, let's briefly review what is the concept of SUID. So the idea is that when we have an executable file, these files can have special permissions on their execute bit, which is called the SUID and GUID bit. So SUID here stands for set user ID, while GUID is for set group ID, so not user but group, because a SUID acts on the permission of the owner of the file, while the GUID acts on the permission of the group that owns the file. So different sets of permission. Now, when it comes to SUID, binaries that have this bit allow the binary to change user permission during its execution. Specifically, for example, consider the passwd program. So this is a binary that is shipped with Linux distribution. Now, this binary allows you to change the password of your user. In order to allow for users to change their password, this program must edit a sensitive file in Linux, which is called the shadow file, and it is present in the etc/shadow. So it is this particular file, etc shadow. Why is this file important? Because this file contains all the hashes of the password of the user, which are used during authentication. So when you want to authenticate to your Linux system, you give to the system a password. The process that checks the validity of your password computes, starting from the password, the hash of your password, and then it checks if this hash is present in the shadow file. So the shadow file is critical for authenticating users. It means that it must be protected. And indeed, if we check the privileges on this file, we see that only the root user can read and write this file. Everyone else cannot do anything on this file. So this file is highly protected. However, we can use the passwd program as a normal user and it still works, meaning that it still allows us to change our own password. How can this work? Well, because in order to access the shadow file, the passwd has a specific configuration that uses the SUID bit. Indeed, if we check the privileges of the passwd program, we see that here, in the execute bit of the owner of the file, there is an S. And this S means that this binary has this particular SUID permission. Now, I explained all about Linux file system permission in the previous video of the series, so if you don't know about that, go check it out. What is important right now is to understand that certain binaries have this particular permission bit, which allows them to use the permission of the owner of the file, regardless of who started the process. It means that as a simple user, I can start the process, for example as the user Leo, but given that this program has a setUID bit, this program will have access to the root permission. So it means that during its execution, it will act as root for certain moments during its execution. It's sort of like it has the choice to be root, to have root privileges, and it can use this to, for example, edit the shadow file. So this is a snippet of code taken from the passwd, so the source code of the passwd command, and as you can see here, there's this line, setUID 0. Essentially, it's getting the root permissions. It's getting the administrator permission for a limited period of time, just enough to update the shadow file. So that's the idea. So to recap, the SUID permission allow an executable to obtain the privileges of the owner of the executable regardless of who started the executable itself. This is only possible when you have this setUID bit. If the passwd did not have this, then when we start it as a normal user, it would only have access to normal user privileges, which means that it would not be able to set its permission as the root user, and therefore it would not be able to edit the shadow file. This is really important. To actually set this bit on a given executable, we can use the chmod command. So for example, in this case, I have this exec.sh, I do chmod u plus s, it means to the user privileges, to the owner of the file privileges, add the SUID bit, and this transforms the executable bit from an X to an S, meaning that it has SUID, the set user ID. Now, what are the security issues with respect to this system? Because in terms of functionality, there's nothing wrong with what we just described. It allows, for example, users to change their password, right? So this is like very useful. However, when it comes to security, the idea is that having a binary that runs as the owner of the file can be problematic when the owner of said file is the root user. More specifically, if the owner of the file is the root user, we might be able to do a lot of actions that only the root user can do, such as read files owned by root users, or read and write files. So not only read but also write files owned by root. And in general, we might be able to execute arbitrary code as the root user. This, of course, depends on the logic that uses this SUID bit. Because in the example of passwd, the fact that this program has the set user ID bit is not a problem because the logic was carefully crafted to not allow privilege escalation during its execution, unless of course there is an important bug. So the idea is that this program uses root only for a short window of time, and during that window of time everything is controlled and the user cannot change the behavior of the program, cannot change the execution path of the program. This allows a safe usage of the SUID bit. If we instead have a custom binary that is not protected with the SUID bit on and the owner of said custom binary is root, this can be really dangerous because if the logic allows the user, for example, to execute an arbitrary command, then with the SUID bit we're going to execute this command using the root privileges. So anytime we have a binary that has this bit on, we have to be careful on how its internal logic is structured, and we have to make sure that it doesn't allow us to do privilege escalation and to maybe do bypasses like authorization bypasses and stuff like that. This is really critical when we have this particular configuration. Now here I have a simple example of a SUID binary, but before discussing this example, I want to talk about three sets of user IDs, which has the real user ID, the effective user ID, and the saved user ID. Now the idea is that anytime a program executes, you have these sets of identifications that the program can use, depending on various factors. Now the real user ID represents who you really are, therefore who owns the process. If the user Leo executed a specific process, then the real user ID of that process is the user Leo. That's literally who started the command. After that, we find the effective user ID. This is the user that is used when the operating system has to make an authorization decision. This means that if the operating system has to understand if you are allowed to access a file or to execute a command and so on and so forth, instead of looking at the real user ID, it will actually look at the effective user ID. If the effective user ID, for example, is the ID 0, which is the ID of root, it doesn't matter what's your real user ID, because the operating system will allow you to do whatever stuff you want, because your effective user ID is exactly 0. So that's the point. And then we find the saved user ID, which is used when a program running with elevated privileges needs to do some unprivileged work temporarily. So for example, you have a program that runs with root user and you want to lower your privileges. Now, if you want to lower your privileges, you will save into the effective user ID or the real user ID another user ID. For example, the user ID of user Leo. Now, to go back to the root privileges, you want to save into the saved user ID the root ID, which is 0, so that later you can get back to it. Now, an unprivileged process may set its effective user ID to only one of the following: the value of the real, saved, and effective. So like the effective user ID is limited because it is actually the most important one. And an unprivileged process, a process that does not start as root, can only put here a value that was already present in these two others, either real user ID or saved user ID. This means that when a privileged process goes unprivileged for a period of time, as long as it's saved on the saved user ID, the privilege ID, which is 0, then later on, since it can do this by definition, it can just use the saved user ID to go back to root. So this is why the saved user ID is important. In our case, however, we don't really care about the saved user ID. And here I put some reference to Wikipedia. We don't really care about that because in terms of exploitation, we are mostly interested in the effective user ID. Now to continue, here I have an example of a SUID binary that just showcases what I talk about. So consider this code. This is C code. Here we have a bunch of includes. Here we have the main function. And the main function essentially does two things. First, we get some data regarding the real user ID and the effective user ID. And then we try to execute a command, which is trying to call the touch hello. And touch hello is simply used to create a file called hello, an empty file. So the idea is that we want to showcase how, depending on the value of real and effective user ID, the file is created with which permission. So we can take this code and we can compile it as follows. So the code is here, content source. Here I have the code, and now I'm gonna compile it. So here I have the shell. I'm gonna compile it. So I've compiled it. Notice that now this code is owned by Leo. So this is owned by my user. And then I can execute it. I execute it and it says, look, real and effective have both the value of 1000, which is the ID of my user. If I say ID, this is the value of my user Leo. And if I check now the created file hello, it is created with Leo permission because like I'm the owner of the process that creates this file. Now, however, notice what happens when we set the SUID permission and when we change the owner to root. So the idea is that first we're gonna change the owner to root like this, and then we're gonna set the SUID binary permission. Okay, notice now that the binary now is red. It's no longer green because bash is telling us that look, this could be dangerous, so we have to be careful about it. And notice that we have owned by root with the SUID permission on. So let's remove the hello we just created previously. So now there's no hello anymore. And let's just execute again the SUID example. Notice now the difference. If before we had 1000 and 1000 on the real and effective, now the real did not change. It is still 1000, but the effective has become 0. So it is no longer 1000. It means that effectively we are running this program as root. And the consequence of this is that any action we take into this program are gonna be recognized as an action taken by the administrator account. So for example, having created the file hello, now this file is created as the root user. So this is owned by root because as the root user, as the user with effective user ID 0, we created this file. So this is really important. So once again, this brings us to the issue using SUID, because the issue is that we can create file as root, we can modify file as root, and so on and so forth. Now the idea is that in your enumeration of a Linux file system, you might find binaries that are owned by root and that have this SUID permission on. In these cases, to actually exploit the binary and obtain various privileges as root, I suggest you check out the website GTFObins.github.io, because this website contains a list of binaries, and depending on the permission you have, it tells you how to exploit it. So here you just say SUID, and here you have the list of binaries, and for every binaries it tells you, okay, how can you exploit that binary to obtain root, execution, or read permission or write permission into the file system using the SUID binary, using the SUID permission essentially. So for example, in this case, I brought a bunch of examples, 4 specific examples, just to showcase. This exploitation, of course, is binary specific because each binary has its own logic. So for example, we can start with wget. So you can install wget locally as follows. So I do this command and now I have a wget with sudo here, wget. Perfect. Now the actual exploit works as follows. So this is the code. Let's try to understand it. So the idea is that we're going to create a temporary file using the maketemp a command. So this make temp creates a temporary file in the temp directory, and it assigns the file path to a bash variable like this, so that with tf we have the path of the temporary file that has just been created. Then we're gonna make this cmod plus x, so we're gonna make this temporary file executable. Then we're gonna write into this temporary file this command in bash, which is called, this is the shebang that tells you that you want to execute this with a shell interpreter, with an sh interpreter, and this is essentially the command you actually want to execute, which is bin sh. So this is the idea. So now if we check out the content of tf, notice that we have this. So this first thing is saying, okay, look, execute this binary with the sh and the /p. The /p is used to decrease the security level, the way that permissions are handled. The second line is the actual command we want to use, and it simply spawns another shell. So it spawns another shell, which is the bin sh shell. And then finally, the actual exploitation is just we call the wget here, and then we use this particular flag, which is called the use askpass equal the file name with 0. So if we execute this, notice what we get. We get a shell running as root. So the idea, the way it worked, is that the wget program has various flags. Now, since we are running this program as root, we want to find one of those flags, one of those parameters, one of those options that allows us to execute arbitrary code. And in this case, the way forward was with the askpass option, because the use askpass takes in an arbitrary command which is used to handle the password manager. It sort of like specifies the command to execute to get the credentials for doing HTTP requests with wget. So it's sort of like we are hijacking the logic of the program for our own personal benefit, which is that of privilege escalation. Now notice that, of course, this particular exploitation will be very different from others' exploitation. The idea when it comes to SUID exploitation is that each binary has its logic. If the binary is configured with the SUID bit and is owned by root, we're able to execute that logic as the root user. So the next step to actually obtain, for example, a root shell is to understand that logic and understand what in that logic allows us to obtain a root shell, or in general root execution. In the case of the wget command, it is this particular option, the use askpass. So to do it manually, once again, what we did is we copied the binary from the root own file. So right now I'm just gonna copy it as the normal user. Then I create a script, hello.sh, I made it executable. And in this script, essentially, I wrote the following content. So I wrote this first line, this one, and then this second line like this. And then I simply executed the wget here as follows. With the flag use askpass, then pwd to say print working directory, hello.sh, and then 0, like this. And now here I have a shell. Of course, in this case, the shell does not run as root because I did not put the SUID bit on. But in general, with wget, I can get a arbitrary shell. And then once we have the SUID permission, I have a shell as root. So that's the idea with wget. Now, the second example, we are using the program hexdump. And with this example, I want to showcase that not with all program we're able to exploit the SUID logic to obtain code execution. For example, with this program, we can at most obtain file reading as root. So once again, how do we do this? We install the binary with the SUID. So this is like a SUID binary. And then let's say that we have another, let's say that I'm going to move as root and I'm going to create a secret file that is owned by root. Secret. So secret file that is owned by root, I'm going to chmod this to have 600 secret. So secret is like only root can access it, right? So as a normal user, I will never be able to read the secret. Permission denied. However, given that I can use hexdump, how can I do it? I can do hexdump, C, and then I put secret. And this allows me to read a file owned by root. Why is this the case? Because in the logic of hexdump, I am able to read files. And when I have like the logic of the program and I can use root permissions to use that logic, then I'm able to read files by root. So the idea is that you have on the one hand the logic functionalities, functions, and on the other hand you have the permissions. So depending on the logic functions, having permissions as root allows you to do more stuff as root. But sometimes the logic only allows you, for example, to read file. So typically the kind of logic functions are either read, write, or execute. So depending on the kind of permission that a specific binary has, you may be able to execute stuff as root, which is the highest form of privilege, or only read or write stuff as root. So that's the idea. Of course, with something like this, if we, for example, steal an SSH key from the root directory, it could still be good, right? Because at the end of the day, with an SSH key, we can log in as root if it is configured to do so. So even having just readability can become detrimental if you can escalate it with typical attack vectors such as reading SSH keys. Now, the third example here is more interesting. It has to do with ssh-keygen, which is a utility that you can use to generate SSH keys. Now, once again, the first step is to copy into our local folder the SUID version of the binary as follows. So now we have this SUID vulnerable version of this binary. Now, ssh-keygen, in the options that it also offers the options to load a shared library. In Linux, these libraries are called shared object, so like .so. So with the D option, we can load an arbitrary shared object. It means essentially that we can inject in the code of the process arbitrary code. However, we have to wrap that code into an SO object. So how can we do that? Well, here I prepared a malicious example. So this malicious.c. So it's these two functions. Now the important thing is that here there is an init function because I compiled it with the no start files. So there's not the typical main. I go directly with init. And also in this file, there is this function called cgetFunctionList. This is because ssh-keygen expects the shared object that is created to contain this particular symbol. So essentially we have to define a function that is called in this particular way, otherwise we'll get an error. So let's see what error we get. If we comment out this function and we compile everything with this, so here it says, use GCC to compile into a share object with a dash shared, then do not add the startup file, so like do not put the typical main that you see in C application. In this one, I don't want it. I just want an init. It means that I cannot take arguments from the command line. Then this is like an option in the way that the code is organized, position independent code. We don't really care about that. And then we put the output file as the malicious.so, that stands for share object. And here is the input file that contains this code. So we execute this and we obtain this malicious.so, and this is like a share object. Perfect. Then we can say ssh-keygen -d with the malicious so. Notice, however, that in this case we do not get code execution. Why? Because it says, look, this share object does not contain the expected string cgetFunctionList. Because the idea is that when this binary loads the share object, it's gonna extract from the share object a bunch of symbols, and these symbols are specified by strings. In this case, when it tries to extract from the share object the symbol cgetFunctionList, it did not get anything because this share object does not export anything. It does not export this particular symbol. So to fix this program, we have to add an extra function, this cgetFunctionList, with our own logic, of course. We can hijack the logic. It's not really important, the logic. What is important is that this function has, like, it's called this function, and we also have like 2 times the malicious code. We can also have it just in init. It's the same. However, it's useful also to put it 2 times to make sure that it actually gets executed. So we compile it again. So we have a new malicious.sh, and now when I do ssh-keygen with the malicious, so let's say cannot open no such file or directory. So let's try to remove this and let's redo it again. ssh-keygen -d malicious. Okay, so I just had to specify the local path for the -d option. Here before that didn't work, I had this, so like here it actually started, okay. So notice that here before it was not a local path, so I did not understood where it was, but with the dot dash, now with the dot slash, now it understands where to load the malicious share objects, and now we have code execution. Once again, we can execute things as root. Why? Because right now the logic of exploitation had to do with ssh-keygen. ssh-keygen in its logic allows us to load a dynamic library, and we have constructed a malicious dynamic library that when executed allows us to execute our code, which is a simple shell with bin sh-p with system. So as simple as that. And we do this set wd and set gid to make sure that this shell is executed with elevated privileges. And as a fourth and final example, I want to showcase how to exploit two important text editors that are also famous, which are Emacs and Vim. Now, both of them, if you happen to have the SUID binary that runs that particular editor, you can use it to obtain remote code execution. So this is the exploit for Emacs, and down we find the exploit for Vim. The idea essentially is that both of these text editors allows you to execute code. So in the context of Emacs, you can do this, which is -q to not load any configuration, -nw to open a new terminal window, --eval to execute customary Emacs Lisp code, and this Emacs Lisp code executes a new shell. So now I'm just gonna execute it without copying in the current directory, because I have some problem with libraries. But you execute this and you have a shell running as your user. In this case, I'm running as user Leo because the Emacs binary does not have the SUID bit on, the SUID permission. If you also have the SUID permission, you can get root execution, so be careful about that. The same things happen for Vim, essentially. The idea is that with Vim, you can execute arbitrary code. So actually, this specific payload for Vim does not work because I did not compile Vim with Python support. But in general, the idea is you find a binary that has the SUID permission, you go into this site, GTFObins, github.io, and you search for your binary. For example, ZH, APT, Spell, AWS, AWK, and so on and so forth. Once you find the correct binary, you just do the payload that brings you elevated privileges, which could be read privileges, write privileges, or a remote code execution. And we saw a bunch of examples. Now to finish off the video, how do you search for SUID binaries? You can use this command. Find, which is a command used to find file system. You can also say, look, I want to find starting from the root of the file system, which means find in the entire file system all the files that are files, so type F, it must be a file, not a directory. And in terms of permission, as the user permission set to S. So the executable bit of the user is set to S, which means it is used to find the SUID binaries. The same thing can be done for the GUID binaries with the G equal S, -G equal S. And here you say true with this redirection to say all the errors you just put into dev null, because you're not really interested in the errors. So when you reach into a Linux system and you want to do SUID exploitation, you search for all the SUID binaries, and for the ones that you find, you use these GTFObins. Depending on the binary, for example, if you find wget, you can use this. If you find ssh-keygen, you can use this. If you find hexdump, you can use this. If you find Emacs, you can use this, and so on and so forth. So depending on the binary, the specific exploitation is different, because remember, the idea is that with a SUID binary, if it's owned by root also, you are able to execute the logic of the binary as root. And depending on the options that the program offers, for example, loading a dynamic library is an option, or reading a file and printing the bytes in hexdump is another option, or using a specific command to use the password manager is an option. So you want to hijack the specific logic of the program, and if you are able to do that, you will obtain root privileges in read, write, or execute. If you obtain it in execute and you're able to spawn a general shell as root, you are done with privilege escalation. So I hope the video was clear. If you have any problem, just write me in the comments, and to the next video.